We now move to the next module in the course focused on localization and mapping. In this lecture, we will cover scan matching, which is a fundamental building block for map-based navigation approaches. We'll cover the concepts, the math, and the code so you can implement scan matching in your next lab. As always, this course is a team effort with contributions from a variety of individuals. We are grateful for learning from each other. We now move to Module C, focused on map-based methods. And as we can see in the syllabus, scan matching will prepare us for localization, SLAM, and motion planning within a mapped world. In localization, our goal is to determine the position of the ego vehicle, that's yourself, with reference to the world frame. Scan matching is a key building block for most SLAM algorithms which use laser rangefinders or RGB and depth cameras. We will dive into the concepts and implementation of iterative closest point algorithm and its variations. As shown in this figure, given two scans, our goal is to find corresponding scan points between the scan frames and match them to find the transformation between the frames. This tells us how much we have moved and estimates our current location in the world frame. You will understand a research paper on scan matching algorithms, work through the math for data association and alignment, learn how the vanilla ICP algorithm of iterative closest point matching works, and then implement more efficient and faster versions of that. So this will prepare us for SLAM algorithms such as Cartographer, which we will use out of the box. And that's why it's essential that we know what happens under the hood. So the Google Cartographer is a SLAM algorithm. And as we can see in the box marked in red, that scan matching is an essential building block. Later on, we will understand how Cartographer works as a whole and where it captures submaps and then integrates these submaps into a larger map. But scan matching is what works locally and then provides a locally consistent submap. And that's where we will get started with. So once we build a map, we will then learn to estimate our pose using a particle filter. Then we will learn to track a reference trajectory to race along a fast race line. We will be able to drive much faster than the reactive methods that you used before. And this is at least 2 to 3 times faster than that. And then that gets us ready for the second racing competition of this course, which is what we are looking forward to, where you will use map-based methods, localization, and then planning within the map to actually have very agile and very high-speed racing. So let's start our engines and get on with scan matching. In today's lecture, I'll first introduce the concept of localization and its motivations, as well as the specific approach to localization called scan matching using the point-to-line iterative closest point algorithm, which you will implement in your lab. So more formally, the problem of localization is to determine the state, that's the position and the orientation of a robot with respect to the environment. Localization can be done within the global frame of some given map, or it can simply be relative to one's starting position. How far to the left or to the right I am from my initial starting point. So localization is a key component for all methods in this course moving forward. So even if you don't directly implement every building block, we can get started with actually looking at the essential ones today, and then use ready-made, optimized, production-ready SLAM algorithms in the future. So let's start with localization with odometry only, that is relying on an IMU and a wheel encoder in an open loop manner, right? So now we want to be able to locate our position with reference to our initial starting point. In our first attempt for localization, we'll utilize odometry and motion integration. So odometry attempts to localize by starting at a known pose and position and integrates the control and motion measurements to estimate the current pose. In our case of our robot over here, we integrate the dynamics using the information from the VESC, which is the electronic speed controller, perhaps wheel encoders, and an inertial measurement unit. So how this works is that we give commands for the movement via the electronic speed controller. That's the VESC. And this unit translates movement commands into lower level commands that control the acceleration and deceleration of the robot. The VESC keeps track of the acceleration that is achieved. And this is integrated to obtain the velocity. And finally, the velocity is integrated to give us the amount of movement since the robot first started. The issue is that noise occurs at all stages of these measurements. This could be some error in the velocity measurement. For example, maybe the velocity was measured at 4.1 meters per second when it actually was 4.2 meters per second. In this case, the robot will actually have traveled further than it had perceived. Now, having better equipment will no doubt help. However, there is a fundamental limitation of using odometry alone, as it is an open loop estimation approach. And there is no feedback mechanism that allows us to correct for errors in the measurement. Therefore, if there is noise in the measurements, this error will accumulate and increase over time. To get a better understanding of this, let's say that we know our robot starts at an initial location in the world frame. We can give it a command to move forward for a certain amount of time to arrive at the position circled in red. The small group of points represents the distribution of possible positions that the robot has, accounting for the error that can occur in the measurement. How spread out this group of points is represents the uncertainty in our position. Currently, we have a relatively good idea of where our current position is. But notice as the uncertainty increases, if we continue to move in the same direction and the spread of points increases. This becomes more prominent as we tell the robot to turn and proceed downwards. And finally, and after the final turn and going on for a longer time, notice how now the possible positions are so spread out that we no longer are able to determine the correct position of the robot. So here is an example of a robot navigating a building to capture its layout using an IMU and wheel encoders only. The robot is not necessarily well calibrated. So we record a data set of the IMU and wheel encoder recordings and build a map. You can see it does a pretty poor job. The problem here is that the assumption that we have known poses is fundamentally flawed. There is also a systemic error in the odometry causing the robot to seem like it is drifting to the right. So the question is, what is the way to fix this? As it is clear that such a map is useless for any navigation task. So it turns out that the sensor is actually pretty accurate. So the idea is to use the sensor information itself to improve the pose estimate. One technique for doing this is scan matching, as you can see on the right side, or incremental scan alignment. This takes scans which are recorded one after the other in time and tries to align them so that their best match on top of each other is found. This is used to estimate the pose and offers a correction for the odometry information. So we don't use odometry only to estimate the new pose, but align the scans so that their best fit overlap gives us a change from the previous to the current pose. So in every step, we try to find the best pose, say xt star, as in this equation here, which is the product of the observation likelihood given the map that's on the first term within the argmax that we built, the map that we built so far, and the odometry, which is the second term. And we want to maximize this. This is a mixture between how well does the current scan overlap with the map I built so far, which is my previous set of scans, times the uncertainty from my motion model. I still want to take odometry into account as a coarse grain reference for the pose and use that as an initialization in my search in scan matching. But then I want to use the LIDAR scan matching for fine grain pose correction and then feedback. So let's take a look at this illustration over here. On the left, we show a robot taking successive scans as it moves through the world. On the right, we have two poses of the robot, each with its associated scan. Our goal is to align these two scans so they have maximum overlap. So one way to search for the best overlap is to do it exhaustively by incremental alignment. Here, each tile shows the likelihood of an XY translation for a fixed rotation angle. The color value at the center of these tiles shows the extent of the overlap between the scans. This also serves as our cost function. So this approach is an extensive search of moving the robot position, say by 1 centimeter to the right, then I evaluate the score. Then I repeat it for 2 centimeters to the right, 3 centimeters, and so on in this grid pattern. And eventually I find a good tile and rotate the robot a bit and repeat the same process until the rotation a bit less or more till I find the maximum value. In this case, this is marked with this arrow over here. So this is my best alignment of the two scans. And this is, one way to do this. There are many ways to maximize, this scan matching function, but this just gives us some initial intuition. So the most prominent approach to scan matching is iterative closest point algorithm, which takes the previous scan and the current scan, and then it makes a data association between the points in each of these and tries to obtain the translation and the rotation, which maximizes the squared distances between these 2 points. As we will see, it uses SVD to do this computation. And there's a zoo of approaches with different cost functions that make point-to-plane alignments, scan-to-scan alignments. Some identify features, to match, and so on. Several approaches, also include ways to eliminate outliers, where points in one scan don't have a partner in the other. This could be done using ransack, for example. In general, scan matching techniques use iterative algorithms for incremental alignment that makes, grid mapping possible. So here's an example of aligning two scans. The blue scan is the reference scan. Then the robot drove a bit ahead and recorded the red scan. Here you see how this alignment procedure aligns between these two scans. Once you find the best match, you take this as your new robot pose and then continue. As the robot moves further, you again match the new scan with the previous one and so on. So this is how we get, to better mapping. It's still not perfect. We see overlaps and the walls are layered on top of each other. So the correction is not perfect, and as the robot keeps repeating through this corridor, you'll start to see even the same room is kind of, jagged in some sense. But this is still much better than the odometer only, correction. So and this is also the minimum we have to do is scan matching in order to build accurate maps. Now we can compare the motion models that we get to, between odometry and scan matching. In red, we see the pose estimate samples generated from a distribution according to odometry. This was a trajectory the robot took, and the sample set represents uncertainty that you have. If you compare that, with the scan matching model in blue, you can see that there's a much smaller uncertainty when compared to the raw odometry model. So things are getting better, right? So in summary, scan matching so far, it improves the pose estimation and thus the mapping substantially. It's good for creating, locally consistent estimates, and, scan matching is not useful for, building large, globally consistent maps, as it is a building block for submaps. So now let's focus on the problem of how, can the car tell where it is in the world in the context of, say, an F1TENTH car going through a corridor, right? So we'll now look at the localization using LIDAR scans for the car driving through a corridor. Here, the car is surrounded by two walls. I show the left wall to be jagged for a reason that will be clear shortly. So now assume the LIDAR is the only sensor on board and the car is driving forward. There are two reference frames to think of. The car reference frame shown in orange is attached to the car, and the world reference frame shown in green, which is fixed and absolute. If we know where the car is now, we can easily transform between the two. At time zero, assume the car knows where it is in the world. Let that absolute position be size 0. The car also has acquired a scan at time 0, and I show part of it, as red dotted lines along the jagged wall. S1 shown in orange is the position of the impact point of beam A1 on the wall. This is expressed in the orange reference frame, but the car knows where it is in the world, that's psi 0. So it's easy to calculate the position of S1 in the world reference frame, that's psi 1, that's S1 of psi 0 shown in green. The important thing to note is that to know S1 in the world frame, we need to know where the car is. That's why the green global S1 depends on psi 0. At time t1, the car acquires a second scan. The question is, where is this when it acquired a scan? It could be shown as over here, or moving to the right, or somewhere else, or anywhere really, without imposing further constraints. We need to figure out where the scan is. So we don't know where the car is, and that's not a good situation. So the premise of scan matching is that the most likely position of the car is the one that gives the greatest match between the previous scene perceived by the LIDAR and the current scene perceived by the LIDAR. Let's see what that means. Remember that the scan is the red dotted line. That's what the LIDAR sees. Scan matching calculates the portions of the two scans that are shown in the black boxes that match very well. If the current position of the car x1, psi 1 is as shown, in fact, this is the best match or the best overlap between the two scans in the world coordinates. So in general, scan matching is posed as an optimization problem. We calculate the position psi star of the car that minimizes the mismatch between the two consecutive scenes, where mismatch is calculated by this sum. For a given candidate position psi, Si of psi I is the world position of impact point I. That's the impact point of step I with an obstacle or the wall in this case. M returns the match of psi I with the previous scene. A match of 1 means a perfect match. Since we have n equal to, say, over 1080 steps, we sum over all of these n steps. As you can imagine, there are many complications to take into account when implementing this algorithm. For example, occlusions mean that an object visible in the previous scene is no longer visible in the current scene. Noise is always a problem. And perhaps will it get better performance if we try to match 5 scenes at a time rather than 2 at a time? Finally, we can and should incorporate knowledge of the car's dynamics. For example, the car cannot do a 180-degree turn in under a second unless something has gone terribly wrong. But then in that case, scan matching won't help you. So all of these are ways to improve the performance of scan matching. Some basic requirements for scan matching to work. First, scanning must happen often enough. Otherwise, there isn't much overlap between consecutive scenes. This isn't really an issue with today's LiDARs that operate at over 20 to 40 FPS frames per second. In fact, it's a good exercise for you to calculate the minimum scan rate that still guarantees some amount of overlap for a given vehicle speed. For example, in the high-speed Indy autonomous racing competition, there seems to be a slight lag in some of the LiDAR scans because the cars are driving over 180 kilometers per hour. That's just an anecdote, but for the LiDARs that we have today, it's not a big issue. Secondly, now this is a bigger issue. Homogeneous surfaces are bad for scan matching, and homogeneous surfaces are basically like smooth surfaces that look the same. So the car thinks that it hasn't moved anywhere. So I'll give you an idea of what this is like. In the US, for example, there's a stretch of Interstate 40 that passes through the panhandle of Texas. The scenery doesn't change much as you drive through, that you might be excused for thinking that you haven't moved at all, because outside the car window, nothing has changed for the last few hours. This is similar to scan matching problem for homogeneous surfaces. The algorithm decides that the best match is provided by psi I1 equals psi I0, no movement. Let's take a look at a live example of this problem. In the next video was taken when the car was actually moving and the video shows that the LIDAR view of the world where the car sees and what it's doing, and the car thinks that it's not moving at all. So the red dots are the LIDAR impact points. Because the surface is too homogeneous, the car thinks that it's immobile, it's not moving. Then because a new different surface appears in the corridor, the car realizes it's moving, but by then it's completely mistaken as to where it is in the world. Finally, one can do the scan matching in a map, given a pre-built map of the environment, right? So the algorithm will match the current scene to scenes in the map. And this way it knows where it is on the map and in the world. In this video, we see the car can tell where it is in the hallway map, which was built on a previous pass through the hallway. So let's understand how scan matching works now under the hood. We'll get some intuition as to how we achieve this kind of map that I've shown before. In this example, the robot with the LiDAR is matching its current scene with the scan from the previous step. Using the single step approach of matching points, it builds a whole map with precise self-localization. Let's look at the vanilla scan matching algorithm that makes this possible. The iterative closest point matching, or ICP, is a technique to align 2 point clouds with each other. Our goal is to compute the transformation between 2 point clouds. These points refer to the real world. So as we align them, we incrementally build a consistent model of the environment. So let's dive into this example and understand how ICP works. ICP basically has 2 steps, a data association step, and then a second step that's computing the transformation to align the scans. In the first step, we want to line the blue and the red points using the simplest, nearest neighbor approach. That means that we iterate over 1 point cloud and look for the closest point in the second point cloud to match with it. In this data association step, which we are matching these points, these are my point correspondences that I have guessed based on this initial configuration. The second step takes this data association and tries to find the transformation so that these 2 points are moved on top of each other, so that the distances of these corresponding points actually gets minimized. This is done using 2 steps. The first step computes the center of mass of the corresponding points. So we shift the point clouds on top of each other. And then the second step computes the optimal rotation using a singular value decomposition-based approach, so that the points are then better aligned with each other. If the scans would match exactly, their cross covariance would be identity. Therefore, we can iteratively optimize that cross covariance to be as close as possible to the identity matrix by applying transformations to the point clouds. Why better, not perfectly aligned? Because our data association may not have been perfect. So what we do is repeat this process, and based on the guesses that we have right now, we compute our data associations, and then we recompute the alignment, and we do this over and over again until the cost is minimized and the lines converge. This is basically the vanilla ICP algorithm. In practice, there are many variants out there on how you can optimize the ICP algorithm. One prominent example is a point-to-line metric, which we will deep dive into later and you will implement in the lab. Here you assume that the points are not distinct points in the environment, but are randomly sampled on a surface. By making an alignment between the point clouds and the surface, we don't create an artificial point-to-point alignment, which may not exist in the real world. And this point, to line alignment gives you a better result of your ICP algorithm. But what it does is that it requires you to leave this SVD-based approach, which is actually simple to compute, and you have to go into general least squares approach. We often have outlier situations where some of the points are really wrongly aligned for whatever reason. To speed up the correspondence search, we have to eliminate these outliers using ransack or robust kernels. So the Jupyter Notebook by Igor Bogoslavsky that is linked on this slide is a good guide to vanilla ICP using the SVD-based approach for alignment and the point-to-line method that uses a least squares approach. So now let's focus on the mechanics of determining this overlap between scans and understand this measurement of closeness between points. We will do this with a very, very basic, simple setup. Let's say that my robot is in some environment where with landmarks A, B, and C. On the left, is a reduced picture of the left-hand side wall, jagged wall that we spoke about before, where we have identified some geometric features and labeled them A, B, and C. These landmarks are fixed in the global frame. Therefore, at time t equal to 0, if measurements of the distance are where A, B, and C are taken, their positions can be localized accordingly as shown to the right. Since we know the actual landmarks, we're able to approximate the reference surface formed by the relative positions as indicated by the line segments connecting A, B, and C. So now the robot has its own local frame of reference where we have the place of origin of the reference at the center line between the two rear points of the body. In the F1TENTH car, this would be the center of the axis connecting the two rear wheels tires. At time 0, the measurements to different landmarks can be shown within the local frame of the robot. Now at time t equals to 1, we assume that the robot has been moving in some unknown direction. Because of this, the distances to the landmarks would have changed. So if we take the measurements to the landmarks A, B, and C, once again, we'll find that they have changed in position as shown over here. The scan matching problem now is to find the transform R that transforms a set of points measured at time step t1 to be the closest to the set of points measured at time step t. Why do we want to do this? This is because the amount required to translate the set of points to match and minimize the distance between them is precisely how much the robot has moved in time, between these time steps t0 and t1. Therefore, the goal of scan matching is to find this transformation R consisting of the translation and rotation in the local frame in order to localize within the global frame. Now, assuming A, B, and C landmarks, obviously made it easy to match points between these two scans. Identifying matching points is actually a very hard problem because some points from the previous scan may have disappeared, or the new in the new scan, or new points have appeared and will not have corresponding points in the previous scan. Occlusions, noise, irregular reflections make this correspondence matching an even harder problem. But for now, we've assumed known correspondences. So the approach that we will take here is to assume the closest points will be corresponding to each other over here, a concept that we call the correspondence match. Based off these correspondence matches, we will iteratively find the best transform R. The way that the iterative algorithm works is that you make some initial guess of R, which we call the current guess. After transforming the points with respect to this guess of R, for each point in the new scan, we find the closest in the previous set of time, t equal to k, a process which we call the correspondence search. Based off the correspondences or the matched tuples of points, the algorithm, makes another better guess of R. So the next guess will be the current guess, and we repeat steps 2 to 4 until the solution converges. To quantify what makes a better guess, we need some sort of metric, which we call the match function, in order to determine, what is a better guess. In order to explain what I mean, by a better transform, we can take this example where we are trying to transform a set of points at t equals 1 to the local reference frame at time t equal to 0. Let's say we have one option, shown in purple, over here on the left, that transforms the points, at t1 in some direction to the left. Another option is transform the points to the right, in this brownish orange. And the question, now becomes, how do you choose between transform, 1 or 2 over here? So in this example, the obvious answer is option 2, but that's because we already knew the point corresponds to A, B, and C, and it's obvious that the points are, at time step t1 end up closer to the points at time step t0 when they're transformed. Even so, we'd like to determine this objectively and use some metric to quantify the distances between these correspondent points. The Nye metric would be, sum up distances between the correspondent points. So we know the correspondence points, and if we sum the distances between the correspondence points, will allow us to determine the transform, 2 results in a smaller value in terms of the metric. However, this method breaks down, when the correspondences are unknown and is sensitive to noise in the measurements, and therefore is not very robust. A better metric would be to use what's called a point-to-point metric. Let's see how this works here. The closest point to B is the point 3. We find the projected point on the line segment, 2 to 3, and the distance, which is B prime. Similarly, if we find the projected distances and sum the squares of each of these projected distances and achieve a score, prime squared, plus B prime squared plus C prime squared, like A prime squared plus B prime squared plus C prime squared, as shown at the bottom over here. Based on this metric, you'll obtain a similar answer where the score of transform 1 will be much greater than the score from transform 2, and therefore you would choose transform 2, which has a better transform now. So the metric we use is the vanilla form of the algorithm called the ICP algorithm. In this algorithm, you initially guess the transform is made, and the corresponding score of the transform according to this point-to-point metric is computed. And then in the next iteration, then the algorithm improves this guess and reduces this value of this metric, and it repeats these iterations of this algorithm until it converges onto a solution. So one thing to note is that the ICP algorithm, is used more generally for, like, say, registration of images or of 2 sets of data that need to be aligned. For instance, in this video, 2 point clouds of a 3D model of a rabbit are aligned using ICP. So now vanilla ICP can be slow, and the initial guess is really important for ICP to converge. Now let's go one step deeper into understanding the transformation required to align 2 points of surfaces, and then we will get into more efficient versions of ICP. For example, given these 2 surfaces over here, at every step we are incrementally getting better alignment, and we assume the data association to be given and then compute this relative transformation. So we're just looking into the alignment step on how to compute this transformation. We have 2 sets of points. We have a point cloud y and the point cloud x consisting of different number of points, and we assume to have this correspondence is given. So the correspondence can be expressed as a set of pairs of indices I and j over here. For example, telling me that the point number 1 in point cloud y corresponds to the point number 10 in point cloud x, for example. And so this is what the correspondences actually tell me. What I want then is I want to find out the translation vector and the rotation matrix, so that T and R, so that I can transform one point cloud x into the coordinate system of the point cloud y, so that the Euclidean distances between the corresponding points in x and y gets minimized. So now I'm actually minimizing the squared error over here for all the corresponding points. So basically we have a sum, summing over the corresponding points, say where the location of this point in the point cloud y, I, and subtract from this the location of the point x transformed into the reference frame of point cloud yi squared. That's the term that I want to minimize. So if I can minimize this expression, I have found the optimal rotation matrix and the optimal translation vector that aligns these 2 point clouds. And if I have zero noise, and I scan exactly the same points, the sum can theoretically be 0. In practice, this is not often the case because, of course, we have noisy measurements around the world, and we cannot guarantee we always measure exactly the same point in the environment as the robot moves through the environment. Although we assume that to be the case here for our correspondence problem, but there's nothing that we can guarantee. So this term is typically not 0, but we want to make it as small as possible. So the key idea is to give those correspondences I'm able to find the rotation and translation for in one go with a direct solution, right? So that's because I am assuming that I have my matches known. And this means that I don't need an initial guess. So assuming that I have the surface, here, where the blue surface and the red surface, and I have a few correspondences here indicated by those lines, I want to find the rotation matrix and the translation matrix so that, the two overlap in this example where the red curve, is transformed to the blue curve, or the curve on the top is transformed to the curve at the bottom in this case over here in a single step, right? So the problem that we are looking into here is actually, a special case of the so-called absolute orientation problem that is frequently used in geodesics. Also in computer vision, which is actually a more complex problem to the problem we are looking at here, where we try to find the similarity transform between two point sets so that the absolute orientation problem, we don't have the rotation matrix in the trans rotation matrix and the translation vector, and we have a scaling parameter. For example, if you're performing 3D reconstruction, from monocular images, and so we don't have the scale information, then we would need such a similarity transform here for the point cloud, and we assume that we know the scale and we don't need to do this for our specific problem. But this is just to show you that there is a general class of absolute orientation problems, and this scan matching is a simplified version of that. So before I want to simplify the notation a bit, especially these correspondences. So I'm not interested in all points in the LIDAR point clouds. I'm only interested in those points where there exist the corresponding partners. So it's a much more reduced set because the others don't contribute to the underlying estimation problem over here. So I'm basically reordering the points in X and Y in a way that I first consider only the points which have a corresponding partner, and then order them in a way that the first point in the point cloud X corresponds to the first point in the point cloud 2 or Y, and second point corresponds to the second point, and so on and so forth. And I basically have an index N which I can use to index point in X as well as in Y, and I can ensure that there's a corresponding point. So this is just a reordering basically of a subset of corresponding points in both point clouds. That doesn't change the problem itself, but it makes the notation easier and much more lightweight. So it's hopefully easier to understand from now on. And I'll not use this set C anymore for the correspondences. I'll just use this index N, so that we have the variable index of N, in point cloud X to match to corresponds to, a point in point cloud Y. And I want to find the rigid body transformation, so I can transform the points in my point cloud X so that I can get, a match in the point cloud Y. So, and this should be done in a way that, the sum of squared errors in the point-to-point errors that remains between X bar N and the corresponding point Yn is minimized. So that's our overall goal over here. The important thing to note here is that a direct solution exists, and a direct solution means that it's not an iterative procedure where I need an initial guess. So I'm completely free, of this initial guess. I can actually come up with a rotation matrix and translation vector that minimizes this term, and so it's also optimal. It's an optimal solution. This means that there exists a no better solution, and I don't need this initial guess, which are two great properties that I have here, as always, and assume that's only because I'm assuming perfect data association, which we can't guarantee in real life, but that's the start of this problem, right? So informally, what this algorithm does, is this approach that it minimizes this function. It basically involves a shift of the 2 point clouds, and I'm shifting them together basically in a way that I'm aligning the center of masses of these point clouds. So basically shifting these point cloud sets so that their center of masses overlap. And then I'm performing a rotation that minimizes the error, not changing this rotation point anymore, so that, any kind of so that it gives me the best match. So So what I can now look at over here is a direct solution says that I need to compute the mean, or in this case, the weighted mean of my point, that y, and my point set x, which is shown over here. So indicated as y0 and x0. So it's just a weighted sum of the points itself. And then I'm using those weighted sums and compute the so-called cross covariance matrix. So I'm taking the points set y, subtract the mean from the points, and do the same in x. And then I compute the outer product of these vectors, summing all of them up together with the weight. And this gives me the cross correlation matrix H over here. Then I'm taking this matrix H and perform a singular value decomposition of H. So I'm decomposing H into three matrices, into the matrix U, into a matrix D, the diagonal matrix, and into a matrix V. So V transposed over here. So we have the SVD is a standard mathematical procedure that decomposes these matrix H into three matrices with these special properties. And then I can compute my rotation matrix as V times U transpose, so the first and the last matrix, and the result of this SVD, right? So, and this gives me my optimal rotation. I haven't explained to you why this is the case. That's something that we can do offline, but I just want to show you that there is a solution that exists over here. So I'm computing the center of masses, and I compute this matrix H, compute the SVD, and from the result of this SVD, I can extract the optimal rotation matrix. And we can do this in a similar way for the translation vector here. So we again use the center of mass of the point clouds X and Y, and then we have the rotation matrix that we have computed in the last step. And then the translation vector is simply given by Y0, right? So, so the center of mass of the points at Y minus the rotation matrix times the center of mass at the point X. So the weighted mean of this point set X over here, right? So this, brings us to our main algorithm of this lecture, point-to-line iterative closest algorithm, or PL-ICP, that was initially written by Andrea Sensi back in 2009. So compared to the vanilla ICP algorithm, the PL-ICP has two major improvements. The first is going from point-to-point metric to a point-to-line metric that results in fewer iterations for the best match. And the second are some clever tricks for optimizing the speed of this correspondence search, so it actually can be done, and used online. We'll cover that in a supplement lecture. So the first major improvement of the PL-ICP is a change from a point-to-point metric to a point-to-line metric. In order to understand how this improves the performance of scan matching, we'll delve a little deeper into the definitions of both. So given a point in the current scan PIW and its corresponding line segment PJ 0 to 1, the point-to-point measures the distance as the distance to the nearest point in the segment. So in other words, you take the point and project it onto some existing point in the line segment itself, as seen over here. In comparison, the point-to-line measures the distance as the distance to the nearest line containing the segment. So now we project the point onto the line that contains this segment. So we are basically extending this line, this scan, or between the two scan points on either side, so that of this line segment, and then basically we would have a normal and the projection of PI as a normal projection onto this line. So the distance is a perpendicular distance from the point to the extended line segment. In some cases, both approaches may lead to the same distance, but that's not the case in general. The important question is, why is the point-to-line preferable and what makes it more efficient? Understanding why the point-to-line metric improves the speed of the algorithm can be explained by two reasons. The first is from the perspective of one projected point. As can be seen in this figure over here, let's say that we have a reference surface, SREF, as shown in blue. For the point, PI of W and its corresponding projected point PI with point-to-point metric, the contours of the level sets are concentric and centered at the projected point. In comparison with the point-to-line metric, this means that the level sets approximate the actual reference surface much better when compared to the point-to-point metric. This in turn means that we have a more accurate approximation of the error, and that results in a faster convergence. The second reason why using the point-to-line metric is faster can be explained from the perspective of the space of transforms induced by these metrics. Let's assume we have two sets of scans, one at time step t equals k, and one at time step t equals k plus 1. Here, ABC is simply signifying the indexed ordering of the points, as it's not related to the correspondence between the two sets of scans. So let's further assume that we are only searching over the set of transforms which are vertical translations of the points, meaning that we are only moving the points up or down, just for simplicity. We can imagine there are three possible transforms which can be found iteratively from the algorithm beginning at transform q equals 0, and the transform q1, which moves to the set of points at tk plus 1 closer with to tk with respect to the vertical axis. And finally, the transform, Q2. So Q0, Q1, Q2. These are just three arbitrary, possible transforms that we have picked over here. Let's first use the point-to-point metric to evaluate these three transforms. From, point A and transform Q0, the distance to the nearest projected line segment will be A0. Similarly, for point B, the distance to the nearest segment will be B0. And for the point C, the distance to the nearest point will be C0. The score of the transform, Q0, according to the point-to-point metric, will be the squared sum of these segments, which we will show here as D of Q0. We can make a similar computation of the remaining transforms if the score of Q0 is A0 squared plus B0 squared plus C0 squared. And for Q1, where the score will be, A1 squared and so on. And finally, the score of Q2 will be, A2 squared plus B2 squared plus C2 squared. Note that the closest point, for point A with transform Q2 has changed to a different, line segment. The key thing to note is that the score of all three transforms is different. So from the perspective of an iterative algorithm that is searching through possible transformations, each of these transformations are possible candidates which the algorithm must search over. Now let's compare the scores of the same transforms Q0, Q1, and Q2, but using the point-to-line metric. For Q0, the point A is projected onto the nearest line, resulting in the distance AO prime. Similarly, the distance from point B to the nearest line under the transformation Q0 is B0 prime. And for the point C, the distance is C0 prime. The score of Q0 under the point-to-line metric will be, A0 squared plus B0 squared plus C0 squared prime. Right? So as before, if we compute the scores for the remaining transforms, Q1 will have a score as shown over here. And note that, under the point-to-line metric, this is important, the score of the transform Q0 and Q1 are the same. We will score Q2 in a similar fashion. Note that we are assuming that Q2 is a threshold, where the closest line to the point A will change. And thus, in our example, we find that Q0 and Q1 have the same score, while Q2 has a different score. In fact, all transforms from Q0 until Q2, which is the threshold of this change, will have the same score. So thus it's important from the perspective of an iterative algorithm by using this point-to-line metric, since all the transforms starting from Q0 to Q2 will be the same. If the algorithm starts the search from the transform Q0, it will go directly to Q2 in the next iteration. This is illustrated in this figure from the original Sensi paper, where each point represents a possible transform in the space of transforms. Given some different initializations of these transforms, under the point-to-point point-to-point metric, the algorithm will follow the trajectory where each point over here will result in different point-to-point correspondences. In comparison, under the point-to-line metric, all the transforms within the area that have the same point-to-line segments correspondences will be considered equivalent in these boxes that are marked here. Therefore, intuitively, the space of transforms to be searched over is reduced and resulting in faster convergence. Hopefully, the reasons explained here until now has convinced you of the benefits of using point-to-line metric in comparison to the point-to-point metric. So this ends our explanation of providing the intuition of scan matching. In the supplemental lecture, we'll walk through the detail of the math for the PL-ICP algorithm so you can code it in your lab and be able to then execute it as shown over here. So this lecture will follow. This lecture will follow with an additional lecture with details on how to code it. Thank you.